Hello, welcome. Today we are physicists on tour. We are not in the Department of Physics at the University of Oxford, though we both work there. We are in fact at the ISIS Neutron and Muon facility, and I'm Catherine. I'm joined by Dr Andrew Princep. Andy, what can you tell us about where we are?
So the ISIS Neutron and Muon facility is kind of like a giant factory for producing neutrons and muons, which are both fundamental particles.
Okay, why do we want to make those?
So they're both very useful for investigating matter at a sort of atomic scale because they are sort of the same size as atoms themselves. Neutrons obviously make up most atoms, and muons are a bit less familiar to most people, but you can think about them basically as really fat electrons.
And why do we have to come here to make them? Why can't we stay in Oxford?
So like most sort of fundamental physics, you need really big high energy beams of particles if you want to produce more particles. And the way we produce them here is we have what is very much like the CERN facility, a giant particle accelerator. So this is a long series of magnets which make, in this case, some hydrogen atoms go faster and faster and faster into a circle until they're about a third of the speed of light. And then we shoot them into a big brick of tungsten. And this kind of makes some of the tungsten atoms explode. And when they do this, they produce loads of neutrons. And we sort of funnel these neutrons in a long tube of what are essentially mirrors. And this focuses the neutrons into a big beam which we use on some target of some sort.
Okay, so we're firing neutrons at something. What has this got to do with crystals?
So the particular way that neutrons interact with atoms means that you can tell a lot about the atomic structure of a crystal from the way the neutrons scatter off it. So we'll take our little crystal and we'll put it right down the end of our focused beam of neutrons. And we have behind that a huge detector. And this detector tells us exactly where the neutrons hit and also how fast they were going when they did that. And this tells us a lot of information about how the neutrons interacted with that crystal. So this gives us information atomically, essentially.
Information about the crystal?
About the crystal, yeah. And mostly about the atoms that make that crystal up. So here we have the sample environment for the MAPS instrument at ISIS. Behind me there is a sort of hole in the ground because we like to keep the neutrons fairly far away from the people. And in that hole is a sort of big aluminium cylinder, at the bottom of which sits my crystal of yttrium iron garnet, which is the material that I'm looking at.
So what is all this kit that we've got here today?
So most of what you see is just pumps, and we use these to pump the helium, the liquid helium. So what you do is you reduce the pressure of the helium gas, and kind of as a result of this pumping, you can cool the system down to very low temperatures.
And then where do the neutrons come into all this?
So the neutrons come from that bit just back there, which is where the big tungsten target is obviously quite low down. Most of this is just concrete to protect us from the neutrons. And it comes under the floor and hits down there, which is where the crystal is. And then they scatter from there into this thing behind the camera, which is the really big detector that belongs to MAPS.
And how big is the crystal that we're talking about?
The crystal itself is about the size of my thumb.
Okay.
It is actually very large for a single crystal. So if you talk about this in terms of commercial diamonds, for example, I think that's about 40 carats worth of yttrium iron garnet. So if it was a diamond, it would be tremendously expensive, even though it's artificially produced.
So we've moved to somewhere a bit more peaceful now. So hopefully, Andy, you can tell us a bit more about where we are and where we were for the experiment.
So here we have a scale model of how the entire ISIS Neutron and Muon facility works. So this first bit here is what we call a linear accelerator. So this fires some negative hydrogen atoms. So it's a hydrogen with 2 electrons. And these are all accelerated using magnets. And they're fed into this ring here, which is called a synchrotron, which basically is a particle accelerator for making things go faster, but in a circle. Before the negative hydrogens enter the synchrotron, they have to have all their electrons taken away. And they do this by just colliding with a big block of graphite. Once the hydrogens have collided with the graphite, this strips all their electrons away, so you're left with just a positive hydrogen ion, which is basically a proton. So these protons are accelerated about 6 times around the ring till they reach 30% roughly of the speed of light. So they're going pretty fast. They could circle the entire Earth in much less than a second. So the protons will then be kicked out of the synchrotron, and they will travel along this path. First, they will hit a small target, which creates the muons, and then they will hit the big block of tungsten here, which is used to create the neutrons. So as I said previously, essentially when protons hit tungsten, the tungsten explodes and produces some neutrons. These then go out along the various beams, and so this one here is MAPS, where we were before, which is one of the target station 1 beamlines.
Thank you, Andy, for showing us around today. It's been really cool to see the inside of the experiment, see the kind of stuff that you work on, and learn a bit more about how we might go about studying some crystals. But I've got one final question for you. All the time I've been here, I have had to wear this. What is it, and why am I wearing it?
So these are radiation monitoring badges. And essentially what they will do is they will absorb some radiation that's floating around while you walk about the facility. And when you go home, someone will take the badge and they will measure it to see how much radiation it's absorbed. And hopefully it won't be too much. But everybody who comes to this facility has to wear one so that we can make sure that they stay under the sort of legal limit for how much radiation you can absorb during your sort of working life. And usually it's much, much less than you would get even from like a dental x-ray or anything like that. So it's pretty safe.
Well, it's good to know that I have been nice and safe while I've been here. Thank you once again for showing us around ISIS.
It's been my absolute pleasure.